Hello. So, can you guys hear me now? Okay. Okay. I'm sorry. Yeah. So we talk about the biological the neural network is the inspiration of artificial neural network. Okay. I mean at the beginning of this chapter, right? But you know, when the biologists, okay, do certain experiment, they found out that the activation function, okay, implemented in the biological neurons, okay, is kind of like a sigmoid, which is like a S-shape activation function, okay, which are kind of like for example, the sigmoid, the hypertension and the logistic, they are also S-shape. Okay, so actually because of that, okay, the AI researchers, okay, trying very hard to use the sigmoid function, okay, in the neural network for a long period of time, okay, because researchers just think like if God use sigmoid, okay, to create like the the human and all these animals, there must be a reason, right? I mean, but it turns out that the ReLU activation function, okay, generally works much better in artificial neural networks, okay, as I already explained, okay. ReLU is actually, you could probably argue it to be like the most popular, most popular activation function. Okay, so this is one of the cases where the biological, neural network, the biological neural network is was misleading. Okay, or you can probably say this way. Okay, maybe God is afraid like a human to be too smart. Okay, so he decided not to use like the best architecture to design like animals like brain. Okay, otherwise like maybe we'll be much smarter. Okay, than what we are now. I mean, who knows? Yeah, but anyway, this is like they are, as I say, like they are the biological neural network now is considered very different from the artificial neural networks. Okay, so this is one major difference. Okay. So remember I told you that in the backpropagation paper, okay, they propose reverse mode autodiff. And I told you that we are going to talk about what this reverse mode autodiff is. Okay, so here we go. Okay, so for that paper, just for you to understand, for that paper, they proposed this idea, but they didn't really implement it. Okay, it actually wasn't implemented until Google create the TensorFlow, okay, to implement the reverse mode autodiff. Okay, but what reverse mode autodiff is, that's it's basically, as I say, it's a differentiation technique. Okay, so that's since it's differentiation technique, that's probably it's a good time to talk about like different differentiation techniques. Okay, so suppose you have a function like fxy equal to x squared y plus y plus 2. Okay, and you want to do partial derivatives. Okay, remember in our gradient descent, okay, because it's going to be higher dimensional. Okay, to be honest, like in this example, we use only two-dimensional x and y, but in reality, when it's in like a artificial neural networks, okay, the function that we commonly see, okay, it has like so many variables, okay, maybe hundreds of thousands of variables. It's very common, okay, and we want to get the partial derivatives for these functions, okay, in order to perform gradient descent. Okay, so okay, there are 5 different approach we could use, okay, to do differentiation. The first one is manual differentiation. The second one is called symbolic differentiation. The third one is numerical differentiation. The fourth one is forward mode auto diff. The fifth one is reverse mode auto diff. The first 3 are, well, pretty straightforward. Okay, manual differentiation, I think there are 5 rules. I don't think I need to go through all these 5 rules. I mean, you guys, as long as you have taken like college calculus, you know how to do differentiation, right? So for partial differentiation, just remember, you just treat like all the other the variables as constant. Okay, just concentrate on the variable that you are dealing with. For example, if you are doing like a partial differentiation for x, then you can treat y as a constant. Okay, that's about it. Okay, so the other part, I mean, are similar to just regular differentiation. So I just so you guys know how to do it, right? So here just to show you like how we do the partial differentiation for the example I just gave you. Okay, for it's very straightforward, so I will not I will not spend much time here. But okay, this approach obviously can become very tedious for more complex functions. Okay, it is called manual differentiation because it takes a human to involve in the differentiation. Okay, and because it's a human's job, so you run the risk of making mistakes. Okay, the good news is that, okay, because we have rules, right? So these rules can be sort of like implemented into by a computer. Okay, so which is called like symbolic differentiation. So what symbolic differentiation is like this. Okay, so say you have a function gxy equal to 5 plus xy. You first like represent this 5 plus xy in a tree like left hand side. Okay, and now, okay, if it's a plus sign, okay, you need to do partial derivative for both sides. Okay, so on the left hand side, okay, from root, because root is a plus, right? So when you do the partial differentiation, because it's like the sum of 2 functions, so basically just try to get like a partial differentiation of both sides. That's it. And the left hand side is 5. So when you do the partial differentiation on 5, it's 0. On the right hand side is multiplication, right? When it's multiplication, then we change it to be like a plus, and it's going to be like the first one, the first term derivative times the second term. I'm sorry. Plus, okay, I mean, and the other part is the first term times the derivative of a second term. So basically just replace each node with, I mean, using the rule that we just had. So it's very straightforward as well. Okay, so obviously, okay, for a small tree like left hand side, okay, with this symbolic differentiation technique, Okay, even though it's done automatically by the computer, it could be grow into a big tree. Okay, very easily, especially if your function has a lot of multiplications. Okay, so but obviously you can also like simplify the tree on the right hand side. Okay, I mean if you can prune it a little bit, for example, like if anything multiplied by 0 is going to be 0, right? So you know that. So for example, like this part is gone. Okay, this subtree is gone. Okay, because it's a 0 times something. Okay, so and if something plus 0, it's going to be just, you can prune this left branch as well. So the result is going to be just a y. Okay, very simple y. Okay, so yeah, with a certain, if you implement the pruning technique, it's going to work reasonably okay. Okay, so so this symbolic differentiation technique works fine, but first it need, I mean, it needs certain simplification. Second, okay, if you try to get like, for example, partial g, partial x, you need one graph, right? And if you do another partial g, partial y, you will need to do it again. Okay, it's going to come out with another tree structure, and you need to prune it again. Okay, so yeah, it takes quite some time. Okay, if you have a lot of different variables there. Okay, so that's like the issue for this um, symbolic differentiation. Okay, the third one is the another issue for the symbolic differentiation is that okay, it cannot deal with like a function that is defined by, for example, like a function, a computer program. For example, like this function, my function. Okay, it obviously this function looks strange, a little bit strange, right? But if you try to use symbolic differentiation, it doesn't work. Okay, for function like this, unfortunately. Okay, so another approach is called the numerical differentiation. Like we all know that the differentiation is pretty much can be in, treated as like something like this, right? I mean, so I mean, you just try to use a very small epsilon, okay, and you are able to compute the differentiation value, okay, at a certain location, of course, okay. So so for example, okay, assume that your function is like x squared y plus 2, this one. Remember we use this one, x squared y plus 2, and then we can use numerical differentiation. Okay, we define fxy first, and then we define the derivative of fxy. Okay, and we add this x epsilon, y epsilon. Okay, then to be something like this, and then when we want the DFD, partial f, partial x, we just use a very small value for x epsilon, okay, and the y epsilon to set to be 0. And if you want the partial f, partial y, you just call the derivative f 3, 4, and set the x epsilon to be 0 and y epsilon to be a small small value, and it will compute the partial derivative for the f at the location 3, 4 for you. Okay, so this is obviously a very easy way to compute the partial differentiation. You don't need even symbolic differentiation. Okay, and it works obviously for any way, any function that you defined. Okay, by as long as it's computable, right? But the issue with numerical differentiation is that it's not so accurate, right? It can only give you approximation. Okay, the result is supposed to be 24 and the 10, but as you can see, after the computation, it gives you these values. Okay, well, it's close to 24 and the 10, but it is not exactly the right value, right? So this is the first issue. And then the second issue is that, okay, look at here. When you call this derivative f3, 4, 0, 0.001 and 0, okay, because it's going to call this derivative, okay, function you defined, right? So basically you are going to compute this f twice, right? And you call the partial f, partial y, you put these numbers there, it's going to call the f again twice. So supposedly, okay, if you have like here, because we have two variable x and y, so to compute the partial x, you call f twice. To compute the partial y, you call the f twice. Okay, if you have like 1,000 variables, okay, the worst case is that you are going to call the function f 2,000 times, right? Of course, I mean, if you observe like very carefully, you will see that, okay, because this fxy is going to be used all the time, right? You can only just compute this once and use it like for different partial derivatives. So yeah, I mean, in that case, if you have 1,000 like variables, then you will call f 1,001 times. Okay, so this this computation is still linear to the number of variables, right? So we still consider this inefficient. Okay, we consider this inefficient. So is there any way that we can, work around with these problems? Okay, so there are, so far for numerical differentiation, we have two issues. First is inaccurate, right? The second one is like it's not efficient. So let's see if we can first solve the first problem, the inaccurate problem. Oh, the advantage of numerical differentiation. It works for like, it's very simple. And so you can use it as a tool to check like if any method you implement are correct or not. Okay, so this is like an advantage of numerical differentiation. Okay. So now, okay, the next approach is called forward mode auto-diff. What exactly is forward mode auto-diff? Okay. The forward mode auto-diff is not symbolic differentiation, okay? And it's not numerical differentiation, but you could say it's their love child, okay? They are conceptually has some connection to these two approaches. Okay, so it relies on dual numbers. Okay, dual numbers. So we would write a number as a plus b epsilon. Okay, a plus b epsilon. So a number is represented as a A-B pair. Okay, where A is a regular number and the B epsilon. Okay, where this epsilon is a very, very small number. Okay, we consider epsilon to be a very, very small number. So anything multiplied to epsilon is considered very, very small. Okay, so it is so small that when this epsilon gets squared, okay, such as epsilon squared, okay, we can just we just consider epsilon squared to be 0. Okay, so conceptually, okay, or like intuitively, you can think of this dual number, for example, 42 plus 24 epsilon as something like 42.0000 many zeros, and we have 24 at the end. Okay, I'm not saying this is the exact the correct idea, but I'm saying this is a good intuition. Okay, so dual number is represented in memory as a pair of floats. Okay, just AB. Okay, so 24 plus 24, 42 plus 24 epsilon just represented as 42, 24 in the memory. Okay. There are some operations for these dual numbers. When a dual number is multiplied by a lambda, it's going to just to be lambda A plus lambda B epsilon. Okay, and then when two dual number, okay, add up, okay, A plus B epsilon plus C plus D epsilon, it's going to be A plus C plus B plus D epsilon. This is very straightforward, right? And when two dual number multiplied together, it's just like regular multiplication. The only thing that is important is that this term, because it has an epsilon square. Remember, I told you epsilon is so small when we have an epsilon square. This term pretty much vanish. So the result is going to be AC plus AD plus BC epsilon. Okay, so far so good, right? So you may not, up to now, you may have no idea why this dual number can be used to solve the partial differentiation. Okay. Then, okay. Do you know this formula? HA plus B epsilon equal to HA plus B times H prime A times epsilon. This may not be look like so obvious to you, so I will how do I open a whiteboard? Okay, let me use a point here. Let's see if I can write. Okay, we know like H. Oh, this look ugly. H prime A. How come it doesn't? Hate it. Doesn't work. Shoot. whiteboard. Hmm? Oh, here. Okay. We know like can you see the whiteboard? Okay, good. Okay. Let me. Okay. Where is it? This is obvious, right? This is obvious. Okay. H prime A equal to H A plus BE. This E is epsilon. Okay, sorry. I mean, I cannot type like epsilon like easily. Okay, just use E as epsilon. Okay, A plus B epsilon minus HA divided by BE, right? Okay, according to the limit theorem, right? Like the derivative is just like the right hand side, right? Because remember the epsilon is very small value. Okay, then okay, you multiply, you try to put this multiply the denominator to the left hand side. Okay, and then you move the minus HA to the left hand side, and you are going to get this. You are going to get this, right? So this is this function, this formula is really obtained from the limit theorem. Okay, or the formula we use for the numerical differentiation. Okay, so we know H A plus epsilon. Okay, will give you both HA and the derivative H prime A in just one shot. Okay, this is very interesting. Okay, let's see how it works. Okay, so this is a figure that show you the. Remember, we have like a x squared y plus 2, right? So this is pretty much the path tree for that function. And then for the x, here, if you want to compute the partial x, okay, you put remember it's you want to compute the location, the partial derivative of at the location 3, 4. So we put the 3 plus epsilon at the location x, and the y to be 4. So this multiplication, well, it's going to give you 9 plus 6 epsilon. Well, plus epsilon squared, but epsilon squared no, it's gone. Okay, and y is 4, right? So 4 times this we have 36 plus 24 epsilon. And we have y plus 2 here, right? So it's 6 here. And then we have like a multiple, we add up these two to get 42 plus 24 epsilon. So you can see 42 is F34, and 24 is the partial derivative of F over X at the location 34, the exact value. Okay, and if you want to get the partial F partial Y at this location, you just put the X to be 3 and the Y to be 4 plus epsilon. And you are going to get F34 and the partial F partial Y34. No, with one evaluation. So I hope like this is clear to you guys. Okay, so this is cool, right? This idea is called forward mode autodiff. So it pretty much solved the inaccurate problem that we had in the numerical differentiation. Okay. But there's still issue, okay? Because yeah, you don't need like a lot of different trees, okay? Like symbolic differentiation when we evaluate like a different partial derivatives. But regardlessly, okay, for one partial differentiation, we need to pass this tree once. So if we have like if we have 1,000 variables, then we need to go through this tree 1,000 times, right? So this is like still inefficient. Okay, it's still inefficient. So so this is where the reverse mode autodiff shines. Okay, it is like so efficient. It's accurate and efficient. Okay, it can compute all of these values in just 2 passes through the graph. Okay, so this is like the best approach. You really cannot beat this reverse mode autodiff. Okay, so what is reverse mode autodiff? Before I talk about the reverse mode autodiff, I want to tell you, I want to make sure you guys know this formula, right? Partial F partial X equal to partial F partial Ni times partial Ni partial X. You know this, right? This is called Chen Rule. I hope you guys, still remember this Chen Rule from your college calculus. I mean, you probably learned Chen Rule from not necessarily in the differentiation part, but from like integration. When the teacher, the calculus teacher teach like we taught like integral. Okay, but nevertheless, okay, the Chen Rule is Chen Rule. Okay, it should be reasonably easy. Okay, no matter you understand it from symbolically speaking or like conceptually speaking, it should be very easy to understand. Okay, so then, what is reverse mode autodiff? Let's we first, okay, give each node a different name. Okay, so you see the X we call it N1. For Y we call it N2. For 2, we call it N3. For the X square, this node obviously, I mean, it's X times X, it's X squared, right? We call it N4, okay? And then this node represent X squared Y, we call it N5. For this one, it's Y plus 2, we call it N6. And the root, we call it N7. So far, so good, right? We just try to give a name for different node, okay, for each node, that's it. And after this naming, obviously, N7 is the same as function f, right? Because the root is function f, right? And the N1 is pretty much x. N2 is pretty much y, right? I hope like it's easy to understand. Okay, and then let's have a look. Okay, partial f partial N7 is going to be 1, right? No question about that. Because, well, f is N7, right? So we know that for sure. Okay. And then partial f partial N5. Okay. Partial f partial N5 is, remember, N7 is the N5 plus N6, right? N7 is, I'm sorry, N5 plus N6. So partial f partial N5 is going to be, you know, partial f partial N7 times partial N7 partial N5. Partial f partial N7 is 1, that we already know. And partial N7 partial N5 is 1, right? Because N7 is N5 plus N6, right? So N6 has nothing to do with N5, so it's going to be 1. So 1 times 1 is 1. So far, so good, right? Okay, and let's go down here. Partial f partial N4. Okay, it's going to be partial f partial N5 times partial N5 partial N4. Okay, and the partial f partial N5, we already get it to be 1. So we put it 1 here. Partial N5 partial N4. So, well, N5 is like N4 times N2, right? N4 times N2. N4 times N2 partial N4 is going to be N2, right? So it's going to be 1 times N2. 1 times N2. And we happen to know N2 is Y, right? Which is 4, because we are looking for the value at location 3, 4. So Y is 4. So 1 times N2 is 4. So it's going to be 4. So so last one. Okay, when we go down, partial f partial x actually is partial f partial N1 is partial f partial x equal to what? Equal to N1, okay, times N4 plus N1 times N4. So the result is 24. Okay. Because like, well, it's going to be partial f partial N4 times partial N4 partial N1. Okay, because and we have two different paths, so we need to add them up. So that's the, I mean, that's the reason we have this. Okay, we have 2 paths, so we add up these 2 paths, so we get 24. And the other part, the other branch, are pretty much the same. So you get like, you know, you can, with this like, with this naming and the go pass all this, you get like a partial f partial x and partial f partial y all together. So this is very, very powerful technique. Okay. this one is same. Okay, you get the value from here as well as value from here. You need to add them up. Okay, so this is called reverse mode order diff. It simultaneously give you partial f, partial x, and partial f, partial y, with just a very simple operations. Okay, as long as you know how to utilize the this Chen Rule. Okay, but so here we talk about like how this second pass works, but I think I already told you about this. So reverse mode order diff is a very powerful and accurate technique, especially when there are many inputs and a few outputs. Okay, this is like always the case for the training in the neural networks. Okay, we have so many input or so many variables, but a few outputs. Okay, the variable can be like thousands of variables, but we only have like a few outputs. The number of output actually depends on your task. Okay, if it's like a regression, it's how many number you want to predict. If it's like a classification, okay, it depends on number of classes, but it's not going to be too many anyway. Okay, and you require only one forward pass plus one reverse pass for output to compute all the partial derivatives for all outputs with regards to all the inputs. And also it can deal with functions defined by arbitrary code. So it can also handle functions that are not entirely differentiable, as long as you are asking for the value at the place where it is like it can be differentiated. Okay, so this is a very powerful technique. But you see that this idea has been proposed in 1980. When was that? This idea was proposed by this paper. Sorry. This paper, 1986. But it wasn't get implemented because it's very difficult to implement. It wasn't get implemented until Google's TensorFlow 1.0. It was implemented by a team led by a very famous software engineer called Jeff Dean. I really suggest you guys to search for this guy's name, Jeff Dean, Jeff Dean. He's very special person. There are many important Google project that was like led by this guy. Okay, you can probably say that. I mean, if Google's current status, is at least I would say more than 30% is due to this guy. Okay, so he's considered, if you remember, like we used to say like there are several gods, right, in those big companies. Now, one of the gods at Google is this guy, Jeff Dean. He's very young. Okay, I believe he's even younger than me. Okay, he's like I forgot his late 40s or early 50s. Okay, but he's a young guy. Okay, so so if you implement a new type of operation in TensorFlow, okay, and you want to make it compatible with a reversible autodiff. Okay, remember, as I said, TensorFlow use the reversible autodiff. Okay, then we have to provide a function that is built, that build a subgraph to compute its partial derivative with regards to its input. As an example, okay, if you implement a function that computes the square of its input, such as fx equal to x squared, then you need to provide the corresponding derivative function f prime x equal to 2x. That's relatively easy, right? So, I mean, by providing this derivative function, okay, you are the the TensorFlow is able to extend its reversible autodiff to include your operation, okay, to work with like any other like operations together, okay. So this function does not compute a numerical result, but instead you build a subgraph that will compute the result. So pretty much like even though we are not going to teach TensorFlow directly, TensorFlow, okay, is really about computer graph, okay, because like it treats the computation as a graph. Okay, so it has its advantage, but also it has its disadvantage because it may not look that straightforward for the first timer, okay, but that's one reason. I mean, TensorFlow is not as popular now, but with like Keras, I mean, as its like function, I mean API, hopefully like TensorFlow 2.0 hide its like detailed implementation at the back end. Okay, so let's well, it's already break time, so let's take 10 minutes break. When we come back, we're going to discuss like Keras a little bit. Okay.